disclose any announcements I may have before we get started with the lecture is the homework that I signed before Mardi Gras break is due tonight on position and 5-number summary. Only 5 of 24 of you have opened the assignment, so you have until tonight to do that. Please make sure you get that done. The subsequent quiz is due on Wednesday. We're going to talk about correlation today and perhaps even on Wednesday as well. And all of those due dates are upcoming, as you can see here. But most importantly, our first exam is a week from today. Our first exam's a week from today. That's going to cover everything we're talking about up through correlation. And so what I was going to do was I was going to have a review session on Wednesday, but the basic premise, we're all going to be testing, and I'll send out an email about this. We're testing in the math tutoring lab, which is in the library. So a week from today, we're not meeting here. We're meeting in the tutoring center. If you took Math 105 or 151 before the pandemic happened, you're aware of which room this is. If not, it's that giant lab on the second floor of the library. Again, I'll send out information about this. I can't remember the room number off the top of my head, but that's where we will be testing next week for this exam. So this exam, you'll have your standard class time to complete it. Like I said, it's going to cover everything from the beginning of the semester to the correlation stuff that we talk about today. I'm going to do a review session on Wednesday, and as a collection of formulas, you can use one of those standard index cards. I think I might have some index cards if somebody needs some. I'll have to bring them with me next time, but you can put any formulas you may need on your index card. But you can use your calculator as much or as little as you want. I would recommend you use it a lot because there's a lot of important functionality that we do on it. So that means you need to be aware of how to do various things on the calculator. And I do have everything, every potential thing that we do in this class. I have all the tutorials in the notes, so you do need to make sure you're familiar with how to do those in the calculator. Maybe some more obscure formulas you may just go ahead and jot those down on your note card. But besides for that, I'll probably just end up sending the complete reference of information in regards to this first exam. Send that out in an email, and I'll be talking more about this on Wednesday. So Wednesday, we're not discussing any new material. We're just going to study for this test. So does anyone have any questions about this? And if you have accommodations, you will be getting an email from me shortly. So if you have any accommodations with me, you're going to get an email from me shortly. So I have you somewhere, and I need to email you about setting up your test in another way. But besides for that, homework due tonight, test a week from today. I think that covers it. So from here, we're going to go ahead and pick up with the new material. New material, and the course notes are updated. New materials on correlation. And if you're just now arriving, if you can go ahead and if you can figure out your height in inches and your shoe size, we're going to be using this information later. Just figure it out, jot it down. You don't know your height offhand, I think your driver's license or your ID has that information, or just make up a close enough number. We're just going to build a data set later on. So just jot that down and put that off to the side. We'll come back to that. But what we're talking about in this section is scatter diagrams and the correlation coefficient. So before, we've been really talking about univariate data. And univariate data is just some data set that is, well, just data that's measured by a single variable. So really, we took some sort of variable and measured it by, well, really, we measured by one variable. So pretty much for everybody in here, we only chose one thing to, I suppose, measure all of you by. So by height, that would be one variable. Or by your GPA, that would be another one. Any one of these qualitative or quantitative variables. And now what we focus on is something very important in statistics and in analysis in general, is this idea of correlation between things. Correlation meaning if one thing does something, does that imply that something else is going to do something as well? And so correlation's used a lot. Sometimes we use correlation to determine, this is used a lot by various police forces to determine if there's a correlation between crime rates and seasons or months of the year, to know how to allocate funding. If you're able to find a correlation between a certain time of the year and how many customers you have in your store, and obviously you're not going to hire as many people if you have this confidence that there's a correlation between it being the summer or it being the winter and people buying pool supplies. Things like this, it may seem very simple intuitively, but this idea of correlation, we can measure this. And this is under this category of bivariate data. So really, we're going to be discussing in this whole chapter bivariate data. This is two variables where we're going to measure the correlation between the two. If one changes, does that imply that the other one's going to change? Or do they have no relation whatsoever? And so since we're measuring two things, now we need to have some terminology to distinguish between the two things. So for measuring two variables, now we're talking about response variables and explanatory variables. And well, the response variable is, so the response variable is explained by the explanatory variable, as the namesake suggests. And so what this truly means, the response variable is the dependent variable, and the explanatory variable is the independent variable. So really the response variable is y, and the explanatory variable down here is x. And this is going to come back to help us later on, because the x variable explains the results, and the response is, well, the response to the explanation. So explanatory is an independent variable. The response variable's dependent. It's responsive based off of the x variable. So we have two variables we're measuring. We gave them names. One's an independent variable, one's a dependent variable. One of them is just some data we collect, and then the other one is hopefully some result based off of that initial variable. So the example we're going to do later, we want to see if your height explains your shoe size, and if so, to what degree of certainty does it do so? And to get a visual understanding of this, sometimes we use a scatter diagram. A scatter diagram is where we measure two quantitative data sets and we put them on a graph. And using however the data is distributed on the graph, we use that to determine what the correlation is, if any, between the two variables. So notice how some of the terminology comes into play here. The explanatory variable is on the horizontal axis. Response variable is on the vertical axis, which is a little bit important why we need to identify these things. And so the horizontal axis is the x-axis. Yeah, it's just x and y. You will notice a lot with statistics that there is a lot of algebra that's implicitly being used here. But the algebra, it's not as rigorous as it was in a college algebra class. It's a lot more interpretive. Interpretive. And so we're going to interpret a lot of algebra rather than go into the theory of it. And we'll see this later with linear correlation. So let's move down to example 1 and actually put some of the stuff together. So researchers want to study the correlation between, well, various universities. Out of the total number of applications they receive, they accept a certain percentage of them, and then they deny a certain percentage of them. That's called an acceptance rate. It's just simple as that. And from there, these universities also have statistics regarding 4-year graduation rates. If you started school in a certain semester, in 4 years from that semester, are you done with class? Did you graduate or did you not graduate? If you did, then you're added to this statistic. If not, you're simply not. And so these statistics are done. They're going to be done about your incoming class in a few years. And so this was recorded by 15 different schools. Now, actually, Southeastern is on this data set. Southeastern is actually this one right here, interestingly enough. Southeastern accepts 91% of applicants, and only 40% of those people graduate in 4 years. As opposed to, I think this is one of the bigger names. I think this might have been Tulane, actually. As opposed to Tulane, that only accepts 13%, and then 77% of people graduate in 4 years. And so we wanted to measure the correlation between this. If you're really picky and only accept the best of the best, how does that affect your 4-year graduation rate? And so with all of this, the first question we're going to ask is, which variable is the response variable? Which one's the explanatory variable? And remember, the response variable is x, and the explanatory variable, got that mixed up. The response is y, and the explanatory is x. So in order to create a scatter diagram, we need to know what the x-axis will be labeled as and what the y-axis will be labeled as. And so to do that, well, we need to see which statistic is going to affect, or which variable is going to affect the other. So will an acceptance rate affect the 4-year graduation, or will the 4-year graduation affect the acceptance rate? So what we end up having here, the acceptance rate, and this is more of an intuitive way, there's nothing really scientific to this. The intuition is that the more picky you are with the acceptance rate, the better your graduation rate is going to be. It's the acceptance rate, so the response variable, or the y variable here, this is the acceptance, or I keep getting them mixed up, 4-year graduation rate. So that's the response to the explanatory variable. Which is the acceptance rate. So the acceptance rate explains the graduation rate. That's as simple of terms as it gets. Acceptance rate explains the 4-year graduation rate, or hopefully it does. That's what we're trying to conjecture here. That's what we're trying to show. And with this, we want to create a scattered diagram of the above results. So I have a graph here, and really what this data up top gives us, so what this data gives us is a bunch of ordered pairs. So each one of these columns is giving us a different ordered pair that we're going to plot onto the graph. And it doesn't have to be too perfect. So the first one is 1377. And so wherever 13's at on the x-axis, so 13 would be right here. 77 would be about right up here. And you just do that for every single column, which is an ordered pair. 24 and 79. So 24 is about right there. 79, a little bit higher. And you keep doing this for every single column. 35, it's probably right in the middle here. And 72, probably be right here. 40 and 70, that'll be about right here. 48 and 65. I'll go ahead and just finish the rest of these very fast. Six. Four. 91 and 40. '88 and 46. 66. 35. And two more. 68 and 71. 29 and 70. Again, it doesn't have to be perfect, but it does need to roughly resemble the trend of the data. That is whenever we use a scattered diagram, which again, since we have two variables, an x and a y, that means we have ordered pairs. And with these ordered pairs, we can plot them on a graph. So with that, now we have a rough idea of how and also fill in the labels for the axes as well. It gives us an idea of how the acceptance rate corresponds to the 4-year graduation rate. So notice we're also labeling these axes. That's pretty much it. That's just constructing a scatter diagram. Generally, these are done using technology, but now you have some sort of intuition as to how the technology actually plots these things. And we'll come back to the interpretation of this momentarily. You might have some sort of intuition as to what this trend may imply. But to bring that into a little bit more refined terminology, we talk about linear relations. That's the next important thing here. Linear relations. A linear relation, well, linear relations are if one of the variables increases, then the other variable is going to consequently increase or decrease. It's going to be one or the other. So either one variable goes up, and that implies the other variable is going to go up, or one variable going up means the other one's going to go down. Two variables are positively associated, so kind of breaking down the types of linear relations. They are positively associated if, well, basically, if one variable increases, implies that the other variable increases. And two variables are negatively associated if increasing one variable will decrease the other one. So a good example to think about, as people get older, well, as we all get older, our car insurance premiums are going to decline. So as we get older, that's an increase in age, but car insurance premiums decrease as you get older. You're less of a risk factor, according to insurance companies. This is a negative association. As one increases, the other one proportionately decreases, or inversely decreases. And so for positive association, there is an example we'll look at later that will deal with this. But the first question, just given all of this terminology, leads us to our first question here. Are the variables in the previous example positively associated, negatively associated, or neither? Why? So what we're asking is, are the variables between, so the acceptance rate is a variable, the 4-year graduation rate is a variable. Are those two variables positively associated, negatively associated, or neither? This is a question I will pass off to you all to think about. What's that? And why is that? You're exactly right. So just to reiterate what you said, this is, so just to come down here and answer the question, the variables are negatively associated. And there's actually a few different ways to determine this. So the variables are negatively associated. That's referring to the variables in the previous example. And one way you can determine this is by looking at the data set themselves. As the acceptance rate increases, the graduation rate decreases proportionately. Another way you can look at it is by using the scatter diagram. So if I made a rough circle of the data, so the scatter diagram gives us a really good idea of the trend of the data. And one thing that is being noticed here is that the trend, so this circle, this oval that I've drawn, is going in a downwards direction. It's going in a downward direction. This is a negative direction. And so that gives us evidence. This is what a scatter diagram does. It gives us evidence that the data is negatively associated because the data is going downwards in a somewhat linear fashion. So it's not perfectly linear, but the width of the data, so the width of the oval that I drew is relatively thin. It's not perfect, and we will never have a perfect linear relation in any data set we have, but we want to get a good idea of what to expect from the data as a whole. We want to make some sort of expectation. We're not expecting to be perfect. Statistics is never trying to do that, but we're trying to approximate to the best of our ability given some data set. So that's another way we can determine it, is by the trend of the data. And so we can write here verbally, though, as acceptance rate increases, graduation rate decreases. Another thing that could be positively associated, your high school GPA is normally a pretty good indication of your college GPA. The better you did in high school, there's a better chance, not saying it's perfectly true, but statistically there's a better chance, or there's a correlation between your high school GPA and your college GPA. So that would be an example of that. Does anyone have any questions before we move on? If not, let's keep going. So going off of this idea of interpreting scatter diagrams, we're going to move down to example 2 here. And we're going to determine whether each scatter diagram has a linear relation or suggests a linear relation between the two variables. If it is linear, we'll figure out what kind of linearity it is. Is it a positive or a negative one? So look at part A first, this graph on the left. So we don't have any data set. All we have is the scatter diagram. And so I'm going to do what I did last time, sort of lasso this data around this little oval to give us an idea of what the trend of the data looks like. Now this oval, well, the first thing we want to ask is this oval fairly compact? Is the data relatively clustered together, or is everything spread out erratically? And I'd like to argue the former. I think it's very neatly compact within this oval. What would be something more erratic would be if points were all over the place like this. Then I would end up circling the whole graph. But the data is neatly compact within this oval, and this oval has an upward trend. It's going upwards, in other words. So it's linear, or there is a linear relation Think about it this way. Data is compact in the oval. So it's linear, but then furthermore, what sort of linearity is it? Is it positive association or negative association? And it's positive because the oval is going upwards. It's going upwards in a positive direction. In the next section, we're going to replace the oval with an actual line. This line's called a regression line. You might have heard of that before, but we'll talk about that in the next section. So this is a positive association, and it's a positive association because the oval is slanted upwards. Now, what about part B? Now, what's interesting here, so this kind of confused me when I first learned about this, because I would think that this is a linear relation. However, this is not a linear relation because there's no slant to the oval whatsoever. The slant will imply some sort of association here. Since there's no slant, then really what this is telling us, it may be, so it can't be a linear relation if it's not a positive or a negative association. So although the data is compact in the oval, this may not necessarily imply a linear relation. So there is no linear relation here, because although the data is compact in the oval, there's no slant to the data whatsoever. And this makes a little bit more sense if you break down what's going on here. As the explanatory variable increases, the response variable doesn't change at all, which means they're not related. If one of them changes and the other one stays still, they're not related. They're completely disjoint, because this says no matter how much you change on your side, I'm going to stay roughly the same value. And any of those just deviations in data could be simply due to errors in measurements. So this would not be a linear relation because it does not fit the criteria of a positive association or a negative association. So I just wanted to make sure everyone was aware of that. But what this does is this leaves us the question of, well, this seems more so speculative than anything. This seems sort of, all right, well, does this seem compact enough for us to say conclusively that there's a linear relation? So really, we're just speculating. But where does the threshold split a conclusion from a speculation? Because example 2 is kind of a trick question here. Example 2, these are both the same data set. So these are both the same exact data set here. It's just they are scaled. Notice the y-axis is the only difference. The y-axis on the left, it goes from 255 to 280. The other one, everything's clustered in between 50 and 300. But it's the same data set. But we gave 2 different conclusions about the data set. So that doesn't seem very conclusive to me. So really what the scatter diagram does, it suggests if there's a linear relation, but it doesn't concretely prove that a linear relation may exist. So that's why the directions say a linear relation may exist. So we need something more concrete than a scatter diagram. A scatter diagram just gives us an intuition. But to give us a concrete number that we can measure, a number of correlation, is this very important idea called a linear correlation coefficient. Very important idea. This is a number, it's just a single number that measures the strength and the direction of the linear relation. So it measures the strength and the direction of the linear relation. And we denote it R. So it's commonly referred to as R. So if you see R show up in this class, what it's referring to is a measure of correlation. Now, R is always going to be between -1 and 1. So there's a few properties here, one of them being that the linear correlation coefficient is between -1 and 1 inclusive. So that inequality that I highlighted, the closer the absolute value of R is to 1, so the absolute value, which means R could be close to -1 or +1, the stronger the linear relation is. So you're going to do some stuff in the calculator. It's going to pop out a number. And the closer this number is, the closer the absolute value of this number is to 1, the stronger the relation is, which means the more compact the data would be. Now we can break that down further to distinguish between positive and negative association. If R is closer to +1, then there's a positive association. -1, negative association. So hopefully that makes sense intuitively. And if the absolute value is close to 0, the weaker the relation is. So that's how this is distinguished. Not only does it measure how strong two variables are correlated, but it measures also the direction, as in, is there a positive association if R gets close to +1, or is there a negative association if R is close to -1? Now, if you're curious about what the formula is to determine it, you will never have to touch this formula unless you take a fun class which deals with the calculus of statistics, which is Math 380. I wouldn't imagine any of you would want to take that class, but that's the formula if you just like to see how complex formulas in this class. This does give a little hint of a standard, normalization, but we don't have to worry about that. Really, we're going to focus on the calculator version of solving this, which means you should all get out your calculators, because there's one thing I especially need you all to do right now, and you only have to do it once, and it'll be set for life unless you completely factory reset your calculator. It's all described in this paragraph. So we're all going to do it together. So the first thing you have to do when you open up your calculator is press second, and there's catalog right where zero's at. So you press second and 0 ultimately. And you should get this right here, this catalog thing. Whenever you get catalog, you're going to scroll all the way down to something called diagnostic on. So you only have to do this one time. Scroll all the way down to diagnostic on. So remember, catalog is right above where zero's at on your calculator. Once you find diagnostic on, just enter, enter. It will just say done like this. You only have to do this once, and you're set for this whole class. Is anyone not able to find this? I'm going to trust that everyone's able to determine this. Again, you should be able to get diagnostic on and done. If you factory reset your calculator by any chance, here's the steps to do it right here in the notes. But I'm going to assume everyone figured that out, and that's telling the calculator that, hey, I want you to tell me the correlation coefficient when I ask for it. So now that you did that, hopefully, we're going to move on to example 3. In example 3, the data that I'm presenting here, this is the data from the scatter diagram from the previous example. So that these scatter diagrams, they come from the same data set. And so I'm just now placing them here. So what we're doing in essence, because the previous example gave us 2 different measures of linear correlation or lack thereof, this example will find the linear coefficient and tell us once and for all which one's correct. And so really the process for doing this is fairly similar to finding the one variable statistics. So we're going to open up the calculator and go to the place where we input all of our data. Now, this is when it's important for you to determine which one is the explanatory variable and which one is the response variable. The explanatory variable, which is the x-axis, needs to go in L1. The response needs to go in L2. In this problem, they just gave those to us. There's X and there's Y. So I'm going to do exactly that. We'll go ahead and start putting in the explanatory variable values. And then in the next column, simply just put the response variable values. So hopefully you should have just the values inputted. And if you quit out of that, you're going to go exactly, so it's the same process almost for if you were doing one variable or 2 variable statistics, but we're going to utilize a new one. We're going to go to LINREG, which is linear regression. We'll talk more about regression later, but it's going to be the one that says AX plus B. There's technically another one down here that switches where the X goes. Just gonna ignore that one. Just use the first one you see. You're gonna get something, you might get something different than this if you have a fancier calculator. But just to go through that again, just to make sure. Whenever you get to linear regression, AX plus B, just keep pressing enter until everything pops up. You get something that looks like this, or very close to this. You have a fancier calculator, it'll ask you a few more things, just keep pressing enter. And this is going to show up. And I want to make sure everyone got to this point. If you did not get to this point, you can definitely ask me. If you did not turn on your diagnostics, R squared and R will not show up. So if your diagnostics are not turned on, R squared and R are not going to show up. That's why we had to do this whole diagnostic thing earlier. But what this tells us, so it gives us A, B, R squared, and R. And this whole chapter, we're going to use all of those numbers. But for right now, all we care about is R. The linear correlation coefficient is 0.93, and I'm just going to round it 3 decimal places, 0.939. So we found a measure. We took 2 data sets, we put them in the calculator, and it told us that R, which is the measure and direction of correlation, is 0.939. This number is relatively close to 1, which means that this is a positive association. So that's how we're using this number in relation to the properties of the linear correlation coefficient. Because it says the closer R is to +1, the stronger the positive association. We have a number that's pretty close to +1. Close to +1, so that's +1 implies positive association. So it's close to +1, so that implies positive association. That's how you read this. So this measure now distinguishes once and for all. Instead of these scattered diagrams that could be misleading, the linear correlation coefficient will just directly tell us the number. And the scatter diagram just gives us a visualization. Does anyone have any questions before we move on? If not, so the linear correlation coefficient gives us a measure of how strong or weak this correlation is. But how do we know? So let's say if R instead was 0.5. Now 0.5 is kind of close to 1, but it's equally as close to 0. So how do we determine with certainty which way, because it doesn't round up, it doesn't work like that in statistics. Where's the threshold at? We don't want to really make conclusions with just speculation. We want to have some sort of quantitative thresholds to make some sort of accurate conclusion. And so what we're going to do to figure this out, we're going to use Table 2 in the appendix. Now, I did mention that we don't really read the book in this class. You could go in my math lab, there's an e-text there, but I figured I would just throw it on in the notes. So if you open up the notes and go all the way down, the last page is going to have Table 2, so I just put it in the notes. So this is critical values for the correlation coefficient. And what this does is this provides us thresholds for if we're above the threshold. So if our R value is above the threshold, then we could say that there is a correlation, positive correlation or a negative correlation. And we'll talk about how to interpret this momentarily here. But this Table 2 in the appendix is right here in the notes. It's also, if you have the book, in the appendix, it's Table 2 there as well. And so really, I briefly described that process for using the table right here. What you're doing is you're finding the absolute value of your correlation coefficient. So in fact, as I talk about this, we're also going to answer the question if the two variables in example 3 are linearly related. So in the previous example, we're going to state with certainty, not just with speculation. So it says find the absolute value of R and lowercase n. Now R we found to be 0.939, and its absolute value is just the positive version of it, 0.939. Lowercase n, does anyone remember what that symbol represents? Because it means something very specific in this class. Lowercase n is the sample size. It's the number of data values. All right, let's scroll up. How many data values do we have? 1, 2, 3, 4, 5, 6, 7, 8. We had 8. So lowercase n is the sample size. Okay, so we did part A. Okay, so part B. On table 2, so that table I showed you in the notes, find the critical value corresponding to lowercase n. Okay, our lowercase n was 8. So let's go to that table. So I'm going to detour right fast. I'm going to go to the table. And our n value was 8. So guess what the critical value is? It's the number right next to it, 0.707. I'm going to scroll up. Well, let's just remember that number, 0.707. Found that from the table. We're going to scroll right up. The critical value is 0.707. So we found the critical value corresponding to n. That's part B. And then part C, so the critical value is the threshold. As in the linear correlation coefficient, if that is larger than the threshold, so since the absolute value of R is larger than the 0.707 that we found, which means our measure of relation is stronger than the threshold, we conclude a linear relation. If it were smaller than the threshold, we would not conclude a linear relation. In fact, we would say they're not linearly related by this table. And you can furthermore conclude a positive association or a negative association based off of the sign of your R value. If it's positive 939, then you would say positive correlation or positive association. If it were negative, you would say negative. So we would conclude that the two variables from the previous example are, in fact, linearly related instead of just saying, oh, it looks close enough. This gives us a conclusive statement about the correlation between the two. So does anyone have any questions before we move on? If not, let's look at example 4. Because we can also use this idea of the correlation coefficient to match graphs with these corresponding measures. So we have 4 graphs here, and we have these 4 different relations here as well. And so our goal is to pretty much match up the measure with the corresponding graph. I think this one should say, that one should be 3, and this one should be 4. If you printed out the notes, that one should be 3 and that one should be 4. But in any case, so let's kind of dissect this one by one. Now, what does A tell us? So we'll start off with A here. What this tells us, so notice the correlation coefficient is 0.053. Is that close to 0 or is that close to 1? It's close to 0, which means there's not really much of a correlation. Close to 0, so close to 0. Means little or no relation. So let's look at all of these. Which one of these graphs has the least amount of compactness possible? It seems like 4. It seems like the dots are sort of just scattered all over the place, as opposed to everything else, which at least has some sort of compactness here. So A, we would say, is 4. So B, R is just -1, just straight -1. Now, the negative means there's going to be a negative association, and the 1 means that the relation is perfect, which means there's not going to be any deviations. Everything is going to be centered up on the same, in the same alignment. So the negative means that the trend will be downward slanted, and hopefully that isolates one of these, or at least narrows it down to 2. Does anyone have any intuition here? It's going to be the first one. B is the first one. So if anything, notice how this data is as compact as it gets. There's no data that strays away from this alignment. Everything is perfectly aligned on a line because it's a perfect linear relation. And since it's negative, that means that the data would be downward sloping, and this data is in fact downward sloping. So B is just I. And now the next two, they have the same magnitude. The next two have pretty much the same magnitude, but just a different sign. One of them has a positive sign, positive 0.946, and the other one's negative. So we want to correlate the positive one with the oval that's going in the positive direction. So hopefully it's clear that 3 accomplishes this. And then that leaves 2. Because 2, everything's fairly clustered together, but it's slanted downwards. So that would be 2. Anyone have any questions about this? If not, let's move on. So this is where we're going to find if there's any correlation between height and your shoe size. So the way I'm going to do this, I'll see how many data values I can get for in-class people, and then I'll require online if necessary. So I start going around. $66.
11. 66. 6 and 61. 6.5 and 62.
9 and then 64.
11 and 74.
7.5 and 63.
9.5, 67.
10 and 68.
Okay. And I was 11 and that's 70. I don't feel like I'm 70 inches though. Pretty short. I think I did that wrong. Probably much shorter than that. I'll just put 68. Okay. So that seems like a perfect number of data points. So fills up our table pretty well. So we're going to figure out if there is a correlation here or not. So first, we need to figure out the explanatory variable and the response variable. What variable may imply the other? Any suggestions? You think height would be a good indication for shoe size, or shoe size would be a good indication for height?
Probably height, she said.
Yeah, I think in this case, it's kind of, it could technically go either way. But these are things, it's good that we have this discussion because these are things that statisticians talk about. You have to decipher these things. You have to come to this reasoning at some point. And so I'm going to say that the explanatory variable, the independent variable is height. And the response of the height is the shoe size. So notice, even though I had the rows swapped, really it's the interpretation of this that matters. Just because you're presented data in a certain format doesn't necessarily imply you have to follow or want to follow that format. So that means when we draw a scatter diagram, we need to make sure the height is the x-axis and the shoe size is the y-axis. And so what we can go ahead and do, so let's see, how can we generate a good scattered diagram? What would be good bounds to use here? Maybe start at 61. This would be 61. Or maybe, because there's that 74 in here, so maybe let's do 60, 60, 62, 64, 66, 68, 70, 72, 74. And the heights are very concentrated between really 6 and 11. Maybe 6, 7, 8, 9, 10, 11. So that would be 6 through 11, and it just goes by ones. And we just make a scatter diagram of all the columns, like we did in the very beginning. So 66 and 9, 66 and 11, 61, 6, 62 and 6.5, 64 and 9, 64, 9, 74 and 11, 63 and 7.5, 67, 9.5, 68 and 10, 68 and 11. So now we have a scatter diagram, and we can use the scatter diagram, or actually, I guess to not get too far ahead, we can use the scatter diagram to sort of get an idea. So would you all say that there is a positive association here, a negative association, or no relation? What's that? It looks positive. We have one outlier. So sorry to that person. We do have an outlier. Generally, in data sets like these, outliers like that would be either weakened a little bit or got tossed. But if we were to try to throw in the outlier as well, it'd be a little bit difficult. We would get this action, which at least gives us some idea of trend. There's a positive trend here. So, but this doesn't tell us that there is a positive correlation. It suggests that there is a positive correlation. And it doesn't necessarily tell us how strong that correlation is. So instead, what we need to do is we need to determine the linear correlation coefficient, which means we go to the calculator. We go to the calculator and we type all these in. Just make sure, don't type these in the wrong order. You can clear very quickly, like that. Remember, you put the heights first. So you're putting 66, 66, 61, you're putting that in the first column. So don't let the order of the rows trip you up. The heights go in the first one because that is the explanatory variable. 62, 64, 74, 63, 67, 68, another 68, 9, 11, 6, 6.5. Let's see what the linear correlation coefficient is. Stat. Could be linear regression. We get a pretty good positive correlation here, positive association, because what we get from the calculator, provided I typed everything in right, is R is equal to 0.834. So if you're still typing in those data values, maybe that might help. But we got an R value of 0.834. Provided I typed it in right, hopefully you all typed that in, got that same number. But if so, that's a good indication. That is another conclusive, or not conclusive quite yet, but it is strong evidence of positive correlation between your height and your shoe size. Actually, I've just realized I forgot a value over here. I'm just going to ignore that. Actually forgot that. Actually, I already included it in the data value. What was that one? It was 75 and 60. Oh, wait, no. 7.5. Never mind. Technology issues, my fault. Everything's good. There's nothing wrong here. Okay, sorry about that. So we got a pretty good correlation coefficient. So now we say conclusively, does a linear relation exist? So how do we say it conclusively? We have to use that table. So remember the table, we need to figure out the absolute value of R, which is still 0.834. And we need to figure out the sample size, which we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 samples that we used. It's 10 people. Okay. Part B, we need a value from the table. So the table so we had 10 people. Okay, so Now we had 10 people, which corresponds to 0.634. 0.634 is the new threshold, 0.634. Scroll up. 0.634. And so we see that the correlation coefficient is larger. That implies a linear relation. Does anyone have any questions up to this point? So there's a note at the bottom, a very important point actually. Correlation does not imply causation. Causation, just a cause. So it may be true that if one variable increases, then another variable may increase, but that doesn't mean necessarily that one variable increasing immediately implies that the other variable may increase as a cause. And one of these situations is due to lurking variables. So one of the examples the book gave was, so there is a correlation between, I think it was the temperature, the average temperature people leave on in their houses on their AC unit and the crime rate. There's a correlation between that, but there's not a causation, because you affecting the temperature in your house isn't going to lower the crime rate if you lower the temperature, raise the temperature in your house. It's sort of this interesting thing. You can find variables that are correlated with each other, but it may not necessarily mean that one may imply the other. I know there's an example in the homework where it talks about phone usage, how many people own a phone versus the crime rate as well. There's a correlation there, but not a causation, because more people that own a phone might not directly affect the crime rate necessarily. These are things called lurking variables, though. And I think for that one, they said that the economy was a lurking variable. It's kind of this implicit, it's basically, this is where it's a little bit fishy to talk about. It's when both variables share a common theme. So another explanatory variable that explains both of them. So they're both kind of response variables to some unknown explanatory variable. Stuff like that. It's kind of interesting, but really I'm pretty much out of time. So what I think I'm going to do, because I didn't finish this whole chapter, but I did finish the first section. So really the first 7 problems from the homework, I believe it's the first 7, that's somewhere. The first 7 problems from the homework are going to be due Wednesday. The first 7 problems on the homework are going to be due Wednesday. That's the correlation homework. And actually, I might push that back a little bit. I think I'm going to break up in here in my math lab. I think I'm going to break up this correlation homework into 2 sections. The first section is going to be due later, which means we're not going to be doing this quiz. I won't have time to get to finish this to get to the quiz. So I think that means I could spread out some of these due dates. So I think I might make Position there, quiz there, correlation part 1 there. All right, position and 5-number summary, not due tonight anymore, it's due tomorrow. You're welcome. So the homework that was due tonight, I'll change that now so you all feel a little bit better. So I guess it's good that worked out that way. It's now due tomorrow. The homework that was due tonight, now due tomorrow. Correlation homework, I'm going to split that up at another point when I'm not busy. And expect an email from me about all these details probably today or tomorrow. All right, it's 9:15. You all get out of here. Have a good day.